December 16th, 1944, 05:45 hours. Defensive position near Krinkelt, Belgium. Staff Sergeant William Chapman of the 2nd Infantry Division's 38th Regiment pressed himself deeper into the frozen earth as the first shells screamed overhead. The pre-dawn darkness erupted with sound, not the familiar whistle of incoming artillery, but something different. Sharp cracks in the air above the tree line, explosions without impact, airburst patterns that violated every principle of artillery fire Chapman had learned at Fort Benning. 3 meters above the snow-covered ground, a shell detonated. No contact with trees, earth, or structure, just empty air transforming into lethal fragments. Then another, and another. The forest canopy became a killing zone of steel rain, descending from explosions that seemed to trigger themselves at precise heights. Chapman had survived North Africa and Sicily. He understood artillery. Forward observers calculated trajectories. Gunners set time fuses based on estimated flight duration. Shells exploded on impact or after predetermined intervals. What he witnessed in those first minutes of the Battle of the Bulge defied this understanding. Shells were exploding at optimal heights above German infantry positions without appearing to hit anything first. By 0600 hours, as the German 6th Panzer Army's massive offensive crashed into American lines, German infantry advancing through the Ardennes forest encountered something their training manuals never addressed. American artillery shells detonated precisely above their heads with no visible cause. The fragmentation patterns were perfect, optimized for anti-personnel effect at exactly the right altitude to maximize casualties while penetrating overhead cover. German after-action reports from that morning would describe impossible fire and self-thinking shells. They were correct on both counts, though they would not understand why for months to come. The technology creating this effect was America's VT fuze, variable time, though the name was deliberate misdirection. These were not time fuses at all, but proximity fuses containing miniature radar transmitters that sensed distance to targets and detonated at optimal killing range. The same technology that had saved London from Hitler's Von flying bombs 4 months earlier was now being deployed en masse in ground combat for the first time. The Germans advancing through the Ardennes had no intelligence about what they faced. Their assumptions about artillery warfare were about to collide catastrophically with American industrial scientific capability. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. To understand the shock German forces experienced that December morning, we must first understand what they believed about artillery warfare and why those beliefs seemed unshakable. The Wehrmacht's tactical doctrine in 1944 rested on decades of German military thought about artillery. Since the Franco-Prussian War, German theorists had refined principles of indirect fire, time-on-target calculations, and counter-battery procedures. These principles had proven effective across 2 world wars. Artillery shells either exploded on contact with solid objects or after time delays measured by burning fuses. This wasn't theory, it was observable physics. Contact fuses detonated upon impact. Simple, reliable, but limited. A shell striking the ground sent fragments upward and outward in predictable cones. Infantry in trenches or behind cover gained substantial protection. Time fuses, developed in the late 19th century, allowed shells to explode in mid-air after predetermined intervals. Gunners calculated shell flight time based on range, elevation, and atmospheric conditions, then manually set mechanical fuses before loading. The system required precise mathematics and experienced crews. Even under optimal conditions, accuracy remained limited. Estimates suggested that achieving effective airburst fire required approximately 2,000 shells to neutralize 1 hectare of area containing dispersed infantry. German artillery doctrine acknowledged these limitations. The Wehrmacht compensated through concentration of fire, massing guns to saturate target areas with overwhelming shell volume. This approach proved effective in earlier campaigns where Germany possessed artillery superiority. By late 1944, however, German industrial capacity could no longer sustain the massive ammunition expenditures their doctrine required. Shell production had declined 30% since 1943 due to Allied bombing of chemical plants producing explosives. The average German artillery battalion on the Western Front in December 1944 possessed approximately 60% of its authorized ammunition stocks, insufficient for sustained operations. The Germans launching the Ardennes offensive understood these constraints. Field Marshal Walter Model, commanding Army Group B, had calculated that limited ammunition supplies required achieving breakthrough within 48 hours. After that point, artillery support would diminish rapidly. The plan depended on shock, momentum, and the assumption that American forces would respond predictably to conventional artillery preparation. This assumption rested on German intelligence assessments of American technological capabilities, assessments that were fundamentally, catastrophically wrong. German military intelligence in 1944 operated under severe limitations. The Abwehr, Germany's military intelligence service, had been largely dismantled earlier that year following Admiral Wilhelm Canaris's dismissal and arrest. Responsibility for tactical intelligence fell to Fremde Heere West Foreign Armies, West, under Colonel Alexis von Roen. This organization had been decimated by the July 20th bomb plot against Hitler. Von Roen himself would be executed in October 1944 for his peripheral involvement. By December, German intelligence on the Western Front functioned with reduced staffing, limited resources, and leadership terrified of providing pessimistic assessments that might trigger Hitler's wrath. More fundamentally, German intelligence operated within conceptual frameworks that made certain technological developments literally unthinkable. German scientists and engineers were among the world's finest. They had developed jet aircraft, ballistic missiles, and advanced armor. Their theoretical physics led the world in several domains. This very excellence created blind spots. German experts had investigated proximity fuze concepts extensively. Multiple research programs at universities and industrial laboratories had explored using radio, acoustic, or magnetic proximity sensors to trigger artillery shells. Every program concluded that the technical challenges made operational deployment impossible within timeframes relevant to the war. The problems seemed insurmountable. Radio proximity fuses required miniature vacuum tubes capable of surviving 20,000 times gravitational force during firing accelerations that shattered conventional tubes instantly. The fuses needed compact radio transmitters and receivers, stable power sources, and electronic circuits that could withstand not only firing acceleration, but also 15,000 revolutions per minute rotational velocity as shells spun in flight. German physicists calculated that even if these obstacles could be overcome, mass production at scales relevant to modern warfare was economically impossible. A single proximity fuse would require manufacturing precision exceeding that of fine instruments, making each unit prohibitively expensive. These weren't merely pessimistic assessments. They represented sound engineering judgment based on Germany's industrial capabilities in the early 1940s. German industry excelled at precision manufacturing of complex systems in limited quantities, exactly the wrong industrial profile for proximity fuse production. When German intelligence received reports in 1943 suggesting Americans might have developed proximity fuses, technical experts dismissed them as disinformation. The technology, they insisted, was theoretically possible but practically impossible given wartime constraints. This conviction hardened into doctrine. By 1944, German military intelligence simply stopped looking for evidence of American proximity fuses. When the technology appeared in the Pacific theater, German analysts attributed American anti-aircraft success to superior radar fire control, an explanation that fit their understanding of possible technological development. Reports from German forces in France during the Vaune campaign mentioned unusually effective British anti-aircraft fire, but again, analysts attributed this to improved radar and fire control systems rather than fundamentally new fuse technology. The irony was profound. While German scientists concluded proximity fuses were impossible, American industry was producing 40,000 units daily by mid-1944. The program, centered at Johns Hopkins Applied Physics Laboratory under Dr. Merle Tuve's direction, had solved every problem German engineers considered insurmountable. Miniaturized vacuum tubes, developed by Sylvania Electric and Raytheon, survived firing forces through innovative designs, using no glass envelope. Tiny batteries, produced by National Carbon Company, remained stable for years, yet activated instantly. Production techniques developed by over 100 American factories turned devices requiring instrument maker precision into mass-produced commodities. By December 1944, American forces possessed millions of proximity-fused shells. The technology had proven itself in the Pacific, where VT-fused anti-aircraft shells dramatically increased kill rates against Japanese aircraft. In August 1944, British anti-aircraft guns equipped with American VT fuses had achieved 82% interception rates against Vaune flying bombs, effectiveness German observers witnessed but could not explain. Throughout this period, proximity fuses remained among the war's most closely guarded secrets, protected at classification levels matching the Manhattan Project. The decision to employ proximity fuses in ground combat represented calculated risk. Every shell fired carried potential intelligence compromise. If German forces recovered intact fuses, they would gain insight into technology their scientists deemed impossible. This risk had prevented earlier ground deployment. American commanders wanted the weapon available for the Normandy invasion but were overruled. The security risk seemed too great. Through summer and autumn 1944, as Allied forces advanced across France and into Belgium, proximity-fused artillery shells remained in depots, unused despite their potential effectiveness. The German Ardennes offensive changed this calculation. On December 16, 1944, as German forces achieved complete tactical surprise and threatened to split Allied armies, American commanders made the decision. Proximity fuses would be deployed immediately in ground combat. The potential intelligence compromise seemed acceptable given the crisis. Orders went out to artillery units across the Ardennes sector. VT fuses were authorized for immediate use. Strict protocols governed their employment. Fuses would be fired only in areas where German recovery was unlikely over German-held territory during retreats, or in areas subject to immediate American counterattack. Every dud shell had to be accounted for and recovered, if possible. American artillery crews had trained with VT fuses for months, but never employed them in combat. The fuses arrived in distinctive packaging marked with special handling instructions. Loading procedures differed from standard high-explosive shells. Each fuse contained a safety mechanism, preventing premature detonation. The device armed itself only after the shell had traveled a minimum distance and achieved stable flight. Crews received minimal technical information. They knew the shells would explode at optimal height above targets without requiring time fuse calculations. They did not know how this worked. The technology remained compartmentalized even from the soldiers employing it. The effect on German forces was immediate and devastating. Artillery that previously required extensive ranging and adjustment now achieved first-round effectiveness. Forward observers called for fire on German concentrations. Within minutes, shells detonated precisely above targets, sending steel fragments through overhead cover that would have protected against ground-burst shells. German infantry discovered that their standard defensive techniques, taking cover behind trees, in shell holes, behind rubble, provided no protection against fragments descending from above. German after-action reports from the first days of the Ardennes offensive describe confusion and mounting casualties from artillery that behaved inexplicably. Units advancing through forested areas encountered fire that seemed to target the tree canopy, creating killing zones beneath. Soldiers seeking cover in building ruins found shells exploding at rooftop level, fragments penetrating downward. Standard counter-battery procedures proved ineffective. American guns could achieve optimal airburst without the lengthy adjustment period that normally allowed German forces to identify and engage enemy batteries. The psychological impact matched the physical casualties. Veteran German soldiers understood artillery. They had developed instincts for survival, reading trajectories, identifying safe zones, timing movements between salvos. These instincts suddenly became worse than useless. Shells that should have exploded on impact with tree branches instead detonated at perfect height above the ground. Shells that should have required careful time fuse calculation achieved instant airburst effectiveness. German troops began reporting that American artillery seemed guided by some form of intelligence, shells that thought and decided when to explode. Technical officers at German divisional headquarters struggled to explain what their forward units reported. Initial theories focused on improved American radar fire control. Perhaps the Americans had developed automated systems that calculated optimal burst heights with unprecedented accuracy. This explanation satisfied some analysts. It fit within understood technological parameters, but it failed to account for specific observations from the field. American shells were detonating at consistent heights regardless of terrain, weather conditions, or target characteristics. The precision suggested not better calculation but some form of active sensing. A few German officers proposed more radical theories. Perhaps the shells contained barometric fuses that triggered at specific altitudes. This would explain consistent burst heights, but seemed impractical. Barometric fuses were sensitive, expensive, and unreliable in combat conditions. More importantly, German intelligence had no evidence Americans possessed such technology at production scales relevant to artillery warfare. Another theory suggested acoustic fuses triggered by reflected sound waves. German researchers had explored this concept and abandoned it as impractical. Sound propagation varied too much with atmospheric conditions to provide reliable triggering. What none of these theories addressed was the fundamental question: how could Americans deploy any advanced fusing technology in sufficient quantities to equip standard artillery shells? German officers knew their own industrial limitations. Germany struggled to produce enough conventional ammunition. The idea that Americans could mass-produce complex electronic fuses seemed economically absurd. This assumption that advanced technology meant limited production blinded German analysis. They could not conceive of an industrial system capable of producing millions of sophisticated electronic devices as standard ammunition components. The reality would have seemed impossible to German observers. By December 1944, American industry had transformed proximity fuse production into routine manufacturing. The program, initiated in 1940, had required fundamental reorganization of American electronics capabilities. Pre-war, the United States electronics industry focused on consumer products, radios, telephone equipment, basic electrical components. Vacuum tube production totaled approximately 100 million units annually, primarily large tubes for home radios and industrial equipment. The proximity fuse required completely different vacuum tube designs. Standard tubes used glass envelopes far too fragile for artillery service. Designers at Sylvania Electric, working with applied physics laboratory specifications, developed tubes using metal and ceramic construction with no glass components. The tube elements were suspended within metal shells using flexible mounting that absorbed shock forces. Under normal conditions, such tubes would fail quickly due to gas contamination. For proximity fuses, short operational life measured in seconds made this acceptable. The tubes needed only to function during shell flight. Production scaling represented extraordinary achievement. Sylvania's specialized facility in Emporium, Pennsylvania, employed over 5,000 workers producing miniaturized vacuum tubes exclusively for proximity fuses. By peak production in mid-1944, the plant manufactured 400,000 tubes daily. Raytheon's operation in Newton, Massachusetts, added 300,000 daily. Total American production of specialized proximity fuse tubes exceeded 15 million monthly, more than total pre-war American vacuum tube production of all types. This represented complete industrial transformation accomplished in under 4 years. The batteries posed equally complex challenges. Proximity fuses required power sources that remained stable during years of storage, activated instantly when needed, survived 20,000 G-forces during firing, and operated reliably at temperatures from -40 to +60 degrees Celsius. No existing battery technology met these requirements. National Carbon Company, working with Applied Physics Laboratory, developed entirely new battery chemistry using zinc-silver oxide combinations. The batteries incorporated multiple safety features preventing accidental activation. A centrifugal switch, activated by shell rotation during flight, completed the electrical circuit. Until the shell spun at sufficient velocity, the battery remained isolated from fuse circuits. Battery production required dedicated facilities. National Carbon's Fostoria, Ohio plant produced proximity fuse batteries exclusively, manufacturing over 200,000 units daily by late 1944. Each battery underwent multiple quality control tests. Random samples were subjected to firing tests actually fired in artillery pieces to verify survival rates. Rejection rates remained below 2%. Remarkable given production volumes and technical complexity. The batteries cost approximately $3 each to manufacture, more expensive than complete conventional artillery shells, yet considered acceptable given tactical advantages. The electronic circuits, completing the proximity fuse, represented perhaps the most sophisticated element. The fuse contained a miniature radio transmitter broadcasting at 180 MHz frequency. This signal reflected off nearby objects, ground, trees, vehicles, aircraft. A receiver circuit detected reflected signals. When signal strength indicated proximity to large objects, triggering circuits activated the detonator. The entire system occupied space smaller than a coffee cup and weighed less than 2 kilograms. Circuit design required balancing sensitivity against false triggering, too sensitive, and shells would detonate prematurely when passing near trees or terrain features. Insufficient sensitivity meant shells would pass targets before detonating. Engineers solved this through careful tuning of detection thresholds and signal processing circuits. The system ignored static reflections. Ground or terrain, the shell approached at constant rate while responding to dynamic reflections from targets. Additional circuits prevented detonation during initial shell flight, allowing the fuse to arm only after clearing friendly positions. Manufacturing these circuits at scale required American industry to develop entirely new production techniques. Pre-war electronic assembly relied on skilled technicians hand-wiring components. Proximity fuse production demanded assembly line methods producing thousands of identical units daily with consistent quality. Companies like Crosley Corporation, which had manufactured refrigerators and radios before the war, converted facilities to proximity fuse production. Crosley's Cincinnati plant employed over 10,000 workers, producing complete fuse assemblies. By peak production, the plant manufactured 16,000 proximity fuses daily. The production line organization resembled automotive manufacturing more than traditional electronics assembly. Components moved through sequential stations where workers performed specific tasks. One station installed vacuum tubes, the next added battery assemblies, another station wired transmitter circuits. Final stations tested completed fuses using automated equipment that simulated firing conditions. The entire process, from component delivery to packaged fuse, took less than 8 hours. This represented revolutionary change in electronics manufacturing precision devices produced with industrial efficiency. Quality control was unprecedented in scale and rigor. Every proximity fuse underwent electrical testing, verifying transmitter function, receiver sensitivity, and triggering circuit operation. Random samples, 1 in every 1,000, faced destructive testing, including firing in test guns to verify survival. Statistical process control, pioneered in American manufacturing during the 1930s, ensured consistent quality across millions of units. Defect rates dropped from 15% in early production to under 2% by 1944. This quality level, combined with massive production volume, gave American forces capabilities German industry could not match. By December 1944, American ammunition stocks included over 5 million proximity-fused artillery shells of various calibers. The standard American 105mm howitzer backbone of divisional artillery could fire shells equipped with either conventional contact fuses or VT proximity fuses. Selection depended on target type and tactical situation. Against dug-in positions, contact fuses remained preferable, delivering explosive force directly against fortifications. Against personnel in the open or under light cover, proximity fuses provided devastating effectiveness. The ammunition logistics were carefully controlled. Proximity-fused shells arrived in distinctive packaging marked with special codes. Artillery officers received authorization to employ VT ammunition only under specific circumstances. The shells were never to be fired in situations where German recovery seemed likely. If American forces withdrew from positions where VT fuse duds might remain, recovery teams attempted to locate and remove the unexploded ordnance. This security protocol reflected the technology's classification level. Compromise was considered potentially catastrophic to Allied operations. When American artillery deployed proximity fuses during the Ardennes fighting, German forces faced weapon effects beyond their defensive doctrine. On December 17, 1944, as the German 5th Panzer Army pushed toward Bastogne, American artillery from the 10th Armored Division employed VT-fused shells against German infantry concentrations near Longville. The results demonstrated the technology's tactical impact. German infantry advancing through open terrain took casualties at rates 3 to 5 times higher than conventional artillery would have achieved. Forward observers reported that single volleys accomplished what would normally require sustained fire missions. The 10th Armored Division's after-action reports noted that VT ammunition allowed drastically reduced ammunition expenditure while achieving superior results. Where conventional ammunition might require firing 100 rounds to neutralize a company-sized target, VT fuses achieved similar results with 20 to 30 rounds. For American forces fighting outnumbered during the Ardennes offensive's initial phase, this ammunition efficiency proved crucial. Artillery battalions could support more sectors simultaneously while conserving limited shell stocks. German casualty reports from the period reflect proximity fuse effectiveness. Units engaged by VT-fused artillery reported wounded to killed ratios different from conventional artillery. Proximity fuses produced more wounds from fragments descending at steep angles, injuries to head, shoulders, and back rather than legs, and lower body typical of ground-burst shells. German medical units noted unusual wound patterns, but did not initially connect them to new American ammunition types. The cumulative effect, however, became clear in divisional casualty statistics. German units facing American artillery during the Ardennes offensive sustained higher casualties per shell fired than earlier campaigns suggested was normal. By December 20th, as American forces stabilized defensive lines and began preparing counterattacks, proximity fuse deployment expanded. Artillery battalions supporting the defense of Bastogne received authorization for unlimited VT ammunition use. The encircled 101st Airborne Division, supplied by air, received VT-fused shells as priority cargo. On December 23, as weather cleared and Allied air support resumed, American artillery around Bastogne employed proximity fuses in coordinated fire missions, supporting infantry counterattacks. The combination of accurate artillery and air superiority shattered German offensive momentum. German forces attempting to tighten the encirclement around Bastogne encountered artillery that seemed to anticipate their movements. American forward observers, increasingly confident in VT ammunition effectiveness, called for fire with reduced safety margins. Shells detonating precisely above targets meant friendly forces could operate closer to impact areas than conventional artillery permitted. This tactical flexibility allowed American infantry to coordinate closely with artillery support, advancing immediately after fire missions, exploiting German disorganization before defenders recovered. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The German High Command gradually recognized that American artillery had become significantly more effective, but explanations remained elusive. Field Marshal Gerd von Rundstedt, commanding all German forces on the Western Front, requested an intelligence assessment of American artillery capabilities in late December. The resulting report acknowledged improved effectiveness, but attributed it to better training, superior fire control, and overwhelming ammunition supplies. These factors were real American artillery doctrine emphasized rapid, accurate fire supported by excellent communications and generous ammunition allocation, but they did not explain the specific lethality German troops reported. A few captured American artillerymen, interrogated about their ammunition, provided confusing information. Some mentioned special shells or new fuses, but possessed no technical knowledge of how they functioned. One prisoner, a forward observer from the 2nd Infantry Division, mentioned that shells would explode at the right height automatically. German interrogators dismissed this as confusion or deliberate misinformation. The idea of self-adjusting fuses seemed more like science fiction than military technology. The intelligence breakthrough Germans needed came accidentally in late December, though they failed to recognize it. During fighting near Streetvith, German forces overran American ammunition stocks, including several hundred VT-fused shells. The ordnance was transported to rear areas for evaluation. German ammunition experts examined the shells, noted the unusual fuses, but did not immediately recognize their significance. The fuses looked like slightly oversized conventional impact fuses. External inspection revealed nothing about internal electronics. Without specific instructions to disassemble and analyze the fuses carefully, German ordnance officers classified them as standard American ammunition and stored them for potential future use. This failure represented one of the war's most consequential intelligence oversights. Had German experts immediately recognized and analyzed the VT fuses, they would have discovered technology that challenged their assumptions about American industrial capabilities. The knowledge would not have changed the Ardennes offensive's outcome. By late December, German forces had already lost strategic initiative, but it would have provided crucial intelligence about American technological sophistication, with implications for future operations. Instead, the captured fuses sat in German ammunition dumps, their significance unrecognized, while American forces continued employing the technology with increasing confidence. By early January 1945, as American and British forces counterattacked, crushing the German salient, proximity fuses had become standard ammunition for American artillery. Usage restrictions relaxed as the front moved eastward into German territory. Artillery battalions fired VT ammunition freely, no longer constrained by security concerns about German recovery. The technology's effectiveness became increasingly apparent in tactical results. American artillery achieved fire mission objectives with significantly reduced ammunition expenditure. German forces attacking American positions faced defensive fires that inflicted unprecedented casualties. The statistical evidence was compelling. American artillery battalions typically calculated ammunition requirements based on pre-war doctrinal formulas, shells required per target type, adjusted for range, weather, and other factors. These formulas assumed conventional ammunition with contact or time fuses. When VT ammunition became available, battalions discovered they achieved mission objectives with 60 to 70% of the calculated shell requirement. This efficiency improvement represented direct translation of technological superiority into tactical advantage. Fewer shells meant artillery could support more sectors, sustain fire longer, and maintain effectiveness despite limited ammunition supply. German forces facing this improved American artillery developed fatalistic attitudes. Veterans who had survived Eastern Front combat described American firepower as qualitatively different from Soviet artillery. Soviet forces employed overwhelming volume, thousands of guns firing in coordinated barrages that saturated target areas through sheer quantity. American artillery achieved a similar destructive effect, with far fewer guns firing fewer shells, but with much greater precision and consistency. German soldiers darkly joked that American shells were more intelligent than German generals. The shells, at least, knew when to explode. This psychological dimension of proximity fuse warfare deserves emphasis. Beyond the physical casualties and tactical disadvantages, German forces faced weapon systems that violated their understanding of technology. For soldiers trained in Wehrmacht doctrine, artillery followed predictable patterns. Experienced troops learned to assess danger by sound, the whistle of incoming shells, the crump of impacts. They developed survival instincts based on artillery behavior they understood. Proximity fuses undermined these instincts. Shells exploded without warning, at heights that seemed random yet were devastatingly effective. The unpredictability created anxiety beyond normal combat stress. German artillery officers, attempting to counter American fire superiority, found themselves technologically outmatched. German doctrine emphasized counter-battery fire using sound ranging and flash spotting to locate enemy guns, then destroying them with precise fire. This doctrine assumed relatively equal artillery technology on both sides. Against American forces employing VT ammunition, the calculus shifted unfavorably. American guns could achieve mission objectives faster, using fewer shells, then displaced before German counter-battery fire arrived. The speed and efficiency proximity fuses enabled made American artillery less vulnerable to suppression. By February 1945, as Allied forces closed on the Rhine, proximity fuses had become routine in American operations. Artillery planning assumed VT ammunition availability. Fire missions were designed exploiting proximity fuse characteristics, airburst patterns against personnel, sustained fire against vehicle concentrations, harassment fire against supply routes. The technology had transitioned from secret weapon to standard capability in under 3 months. This rapid integration demonstrated both the technology's tactical value and American artillery's organizational flexibility. The production statistics underlying this tactical employment were staggering. From program initiation in 1940 through war's end in 1945, American industry manufactured 22 million proximity fuses of all types. Artillery fuses represented approximately 12 million units, enough to equip over 10% of all American artillery shells produced during the war. The program cost exceeded $1 billion in 1944 currency, approximately $15 billion in contemporary terms. This investment represented a calculated decision that technological superiority justified massive resource allocation. The cost-benefit analysis supported the investment. Each proximity fuse cost approximately $18 to manufacture by late 1944, expensive compared to conventional shells costing around $3 complete. However, tactical effectiveness made the expense worthwhile. Military analysts calculated that proximity fuses increased artillery effectiveness by factors of 3 to 5 depending on target type. In practical terms, an artillery battalion equipped with VT ammunition could accomplish mission objectives 3 battalions with conventional ammunition would require. The force multiplication justified the cost. The full scope of American technological advantage would not become clear to German forces until after the war's end. Throughout the final months of fighting the Rhine crossings, the encirclement of the Ruhr, the final drive into central Germany, German troops continued encountering American artillery that behaved in ways their doctrine could not explain. Reports accumulated describing shells that exploded at optimal heights, fire missions that achieved devastating accuracy with minimal ammunition expenditure, and defensive fires that created impenetrable barriers of air-bursting fragments. Yet German intelligence never connected these observations to a single technological explanation. Part of this failure stemmed from compartmentalized information flow. Wehrmacht units reported tactical observations to their immediate commands. These reports rarely reached higher headquarters in forms that would allow pattern recognition. By spring 1945, German military organization was fragmenting under relentless Allied pressure. Communications broke down. Staff officers focused on immediate crises rather than long-term intelligence assessment. The systematic analysis that might have identified proximity fuses as a unified explanation for observed American artillery effectiveness simply never occurred. More fundamentally, German commanders and technical experts remained trapped by their initial assumptions. They had concluded that proximity fuses were impossible given wartime industrial constraints. This conclusion, reached by competent scientists based on Germany's technological and industrial capabilities, became unquestioned doctrine. When evidence contradicting this doctrine appeared, analysts interpreted it through frameworks that preserved their fundamental assumptions. American artillery was more effective because of better training, superior fire control, overwhelming ammunition supplies. Any explanation seemed more plausible than mass-produced electronic fuses. The psychological investment in this position ran deep. Acknowledging that Americans had achieved what German engineers deemed impossible would require admitting fundamental errors in assessment. It would suggest that American industrial scientific capabilities exceeded German understanding by margins too large to ignore. For a military establishment that prided itself on technical sophistication and engineering excellence, such admission would be devastating. Easier to attribute American success to quantitative advantages, more shells, more guns, more ammunition, than to confront qualitative superiority in the technological domain where Germany considered itself supreme. When Germany surrendered unconditionally on May 8, 1945, thousands of Wehrmacht officers and technical specialists entered Allied custody. Among them were artillery officers who had commanded batteries from the Ardennes to the Rhine, ordnance experts who had analyzed captured American equipment, and intelligence officers who had attempted to assess Allied capabilities. The systematic interrogations that followed would reveal the extent of German ignorance about proximity fuses and the shock German experts experienced upon learning what they had faced. Lieutenant Colonel Herbert Jarry, who had commanded an artillery regiment during the Ardennes offensive, described his interrogation by American technical intelligence officers in June 1945. The Americans asked specific questions about German observations of American artillery effectiveness. Jarry described the unusual airburst patterns, the consistent detonation heights, the reduced ammunition expenditure he had noted. The American interrogators then showed him a proximity fuse the first Jarry had seen, despite months of combat against VT-equipped artillery. His reaction, preserved in interrogation records, was disbelief followed by professional admiration. "We assumed you had perfected time fuses and fire control to extraordinary precision. We never imagined self-sensing shells existed in production quantities." German ordnance specialists brought to American testing facilities for technical interrogations experienced more profound shocks. These were men who had spent careers in ammunition development and production. They understood the theoretical possibilities of proximity fuses. German researchers had explored similar concepts, but they also understood the practical obstacles that had convinced German programs such fuses were not feasible for wartime deployment. Being shown American VT fuses in quantity, learning of production volumes exceeding 20 million units, discovering that manufacture had been routinized to automotive assembly line standards, this contradicted everything they believed possible. Dr. Heinrich Vogel, who had directed proximity fuse research at a Wehrmacht proving ground, was among those interrogated about German knowledge of American VT technology. His responses, recorded in detail, revealed the completeness of German intelligence failure. Vogel confirmed that German researchers had investigated proximity fuses extensively. They had developed prototype acoustic fuses, experimental radio frequency sensors, and barometric triggers. Every program had encountered insurmountable obstacles. Miniaturization proved impossible with available vacuum tubes. Power supplies could not survive firing forces. Production costs made mass deployment economically absurd. German research concluded that proximity fuses might be possible in theory, but were impractical for artillery use during the war. When shown American VT fuses and told of production volumes, Vogel's reaction combined technical admiration with strategic dismay. The miniaturized vacuum tubes alone represented manufacturing achievements he had considered impossible. That Americans had developed these tubes, created reliable batteries, designed functional circuits, and then mass-produced millions of complete fuses, all while fighting a global war, indicated industrial scientific capabilities that dwarfed German equivalents. Vogel estimated that Germany lagged at least 10 years behind American electronics development. More significantly, he suggested that German industrial organization, emphasizing small-scale precision production, could never have achieved the mass production scales American industry accomplished routinely. These interrogations revealed a pattern across German technical specialists. They did not lack scientific knowledge or engineering skill. German physics, chemistry, and engineering were world-class. What they lacked was experience with the kind of industrial scientific integration American industry had developed. German research proceeded from universities and government laboratories to industrial production through sequential steps. American programs, particularly the proximity fuse development, integrated research and production from the beginning. Scientists at Applied Physics Laboratory worked directly with production engineers at manufacturing facilities. Design modifications improving manufacturability occurred continuously. The result was technology optimized not just for performance, but for mass production. This integration reflected broader differences in industrial culture. American industry in the 1940s emphasized standardization, interchangeable parts, and high-volume production legacies of automotive manufacturing practices. German industry valued craftsmanship, precision, and sophisticated engineering excellent for producing advanced weapons in limited quantities, unsuitable for mass-producing complex electronics. The proximity fuse program succeeded because it matched technology to American industrial strengths. Attempting the same program in Germany would have failed not because German scientists were less capable, but because German industrial organization could not support the required production scales. The strategic implications became clearer as post-war analysis progressed. Proximity fuses represented force multiplication, enabling smaller artillery forces to achieve effects previously requiring much larger formations. For the United States, fighting global war on multiple fronts with relatively limited ground forces, such multiplication was essential. American infantry divisions contained less manpower than German equivalents, approximately 15,000 soldiers versus 17,000, but achieved superior combat power through technological advantages like proximity-fused artillery. The VT program was not an isolated wonder weapon but part of a systematic American approach to warfare, emphasizing technology and industrial capacity over manpower. German forces had encountered this approach throughout the war, but never fully understood its implications. In North Africa, American units seemed inexperienced, yet prevailed through material superiority. In Italy, American divisions advanced, despite terrain favoring defense, because artillery and air support compensated for tactical limitations. In France and Germany, American forces pressed forward despite fierce resistance, sustained by logistics and firepower German forces could not match. Proximity fuses were one component of this larger system significant, not because they were miraculous, but because they exemplified American capability to develop, produce, and deploy advanced technology at scales that overwhelmed opponents. The post-war revelation of proximity fuse technology influenced how German officers interpreted their defeat. Many had attributed German losses primarily to numerical superiority. The Allies simply had more men, more tanks, more planes. This explanation preserved German military pride while acknowledging defeat. Learning about proximity fuses complicated this narrative. Here was evidence of qualitative superiority technology Germany had pursued but failed to achieve, deployed by adversaries in quantities that demonstrated industrial dominance. The defeat was not merely numerical but systemic, reflecting fundamental advantages in scientific industrial organization. For American military planners, proximity fuses validated the investment in military scientific integration. The program demonstrated that systematic application of scientific research to military problems could generate decisive tactical advantages. This lesson would shape post-war American military development profoundly. The creation of permanent military research institutions, continued investment in defense technology, and emphasis on maintaining technological superiority all reflected proximity fuse program lessons. The line from the Applied Physics Laboratory in 1940 to modern American defense research establishments runs directly through the VT fuse experience. The technology itself evolved rapidly in post-war years. Proximity fuses developed for artillery, adapted to other applications, anti-aircraft missiles, air-dropped bombs, naval weapons. The basic principle, using sensors to trigger weapons at optimal range rather than relying on impact or timing, became fundamental to modern munitions. Contemporary smart weapons with sophisticated targeting systems descend directly from the simple radio frequency proximity sensors American engineers developed under wartime pressure. The revolution in military technology the proximity fuse initiated continues reshaping warfare 8 decades later. But in December 1944, when proximity fuses first saw large-scale ground combat deployment, none of these long-term implications were apparent. What mattered was immediate tactical effect. American artillery could destroy German forces with unprecedented efficiency. German soldiers faced weapons that seemed to think, shells that knew when to explode. Their officers struggled to explain effectiveness that violated doctrine. Their technical specialists dismissed evidence contradicting their assumptions about what was possible. The result was comprehensive intelligence failure. Germans fought technology they could not recognize even when experiencing its effects directly. The irony was complete. Germany, a nation that prided itself on technical sophistication, faced technology its experts declared impossible. The proximity fuse embodied everything German military-industrial culture struggled to achieve: successful integration of advanced science with mass production, systematic collaboration between researchers and manufacturers, willingness to invest heavily in programs whose outcomes remained uncertain. These were strengths of democratic, market-oriented American society that the totalitarian German system could not replicate. The invisible radio waves triggering shells above German positions represented visible failure of German assumptions about relative technological capabilities. Staff Sergeant William Chapman, who witnessed the first proximity-fused artillery fire of the Ardennes offensive on December 16, 1944, survived the war. In post-war interviews, he described the transition from conventional to VT-fused ammunition as transformative. Artillery became reliable in ways it had never been before. Forward observers gained confidence calling fire danger close to friendly positions because airbursts were predictable. Infantry advanced knowing artillery could support them effectively. The technology, Chapman reflected, gave American forces psychological advantage, matching its tactical benefits. They knew their artillery was superior. German forces sensed this superiority without understanding its source, a deeply demoralizing combination. The German soldiers who advanced through the Ardennes forest that December morning faced not just American resistance, but the full weight of American industrial scientific capability. The shells exploding above their heads with impossible precision carried messages those soldiers could not read. Each airburst detonation announced that American technology had surpassed German understanding. Each fragment descending from empty air declared that German assumptions about relative capabilities were catastrophically wrong. The Wehrmacht was fighting not just an enemy with more resources, but an enemy who had achieved technological breakthroughs German science deemed impossible. By war's end, American forces had fired approximately 4 million proximity-fused artillery shells in ground combat, roughly 30% of total VT fuse production. These shells saved countless American lives by increasing artillery effectiveness and reducing need for close combat. They killed tens of thousands of German soldiers, many of whom died never understanding what weapon had struck them. The shells represented the triumph of American industrial democracy over totalitarian militarism, mass production over craftsmanship, systematic research over isolated genius. They proved that in modern warfare, victory flows to nations that can mobilize entire societies, scientific establishments, industrial capacity, and workforce toward common purpose. The Germans never knew. Through months of combat, facing artillery that grew steadily more effective, they never identified the technology destroying them. They hypothesized, speculated, and theorized, but never arrived at the correct answer. Their scientists had declared proximity fuses impossible. This declaration became unquestioned truth, blinding them to evidence accumulating before their eyes. When shells exploded at perfect heights above targets, German observers attributed it to luck, skill, better calculation, anything but technology their experts insisted could not exist. This cognitive failure ensured strategic surprise was maintained from first deployment through final surrender. The proximity fuse remained classified until September 1945, 4 months after Germany's defeat. The War Department's public announcement described it as one of the most important weapons developed during the war, surpassed in effectiveness only by the atomic bomb. For German technical specialists reading this announcement, the comparison was devastating. The atomic bomb represented the ultimate expression of scientific achievement, theoretical physics transformed into an apocalyptic weapon. That proximity fuses were considered remotely comparable suggested the scale of German technical intelligence failure. They had been fighting weapon systems ranked alongside the century's most significant technological achievement, and they never knew it existed. The announcement initiated a flood of technical publications explaining VT fuse development, production, and deployment. German scientists reading these papers recognized names, vacuum tube designs similar to concepts they had explored, circuit architectures they had considered, manufacturing techniques they had dismissed as impractical. The American achievement lay not in revolutionary physics or unknown engineering principles, but in systematic solution of problems German programs had abandoned. Where German researchers concluded obstacles were insurmountable, American engineers found solutions through persistence, collaboration, and industrial scaling. The lesson was humbling. Technological superiority required more than scientific brilliance. It demanded organizational capability to translate ideas into mass-produced reality. This organizational dimension deserves final emphasis. The proximity fuse succeeded because American society possessed structures enabling large-scale collaboration. Universities conducted basic research. Industrial laboratories developed practical applications. Manufacturing companies created production systems. Government agencies coordinated efforts and provided resources. Labor unions negotiated workforce cooperation. Thousands of workers contributed specialized skills without knowing the final products. This distributed, collaborative approach generated results that the centralized, hierarchical German system could not match. The fuse was not an invention of singular genius, but a product of systematic social organization directed toward a common goal. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.